times meditation. So this is the talk, and so I will be talking about a very old subject in nuclear structure actually, and dealing with seniority. And I thought, well, I give a little bit of historical sort of developments, how seniority came into being. Then I also will show a little bit how it has been used in nuclear physics. This will cover about half of my talk, and then the main, or the second half of my talk will be about a more recent development, and I would like to convince you of the fact that seniority still plays a role in nuclear structure. In particular, there is an interesting twist to conservation of seniority, maybe it can be partial. Okay, so let me begin with a few historical remarks. So seniority was introduced by Racah. And Racah, in the 40s, he wrote a series of 4 papers, which were all called Theory of Complex Spectra. And these were really very important papers. Like, just to give you a flavor of their importance, in 2000, Physical Review selected the 100 most important papers of the 20th century. And so one of those papers was one of the series of Racah. Okay, so in the third of this series, he introduces the notion of seniority. And very strange, it's even not mentioned in the abstract. It's sort of a byproduct of what he does in this paper. But just to convince you that it's actually done in this paper, I'll show you a few extracts. So this is, he introduces an operator here, and this operator is defined with this two-body matrix elements, and that's exactly what we also have in nuclear physics. So when the orbital angular momenta of the electrons, because this is an atomic problem, so when the orbital angular momenta of the electrons are coupled to 0, he assumes it has a non-zero matrix element, and in all other couples, the matrix element is 0. Okay? And then he shows that your wave functions, many body wave functions, can be characterized by a quantum number, and he calls this the seniority number. And he even derives a little formula. So for n electrons, and electrons with a given seniority, he has a closed formula for the energy of that configuration. And so the seniority here, this notation I will follow throughout, is denoted by the Greek letter V, epsilon actually. So V comes from Racah, from Vettek, which is seniority in Hebrew. So what is seniority? So what, in words, you can call it the number of particles which is not in pairs coupled to J plus 0. This is sort of a loose definition. One has to be a bit more careful if you want to do this exactly. You have to do it with CFPs. But I mean, intuitively speaking, it's the number of uncoupled particles, not in pairs coupled to J plus 0. Okay, and so what Racah showed that if you take a pairing interaction, so an interaction which is non-zero if the particles are coupled to J is 0, if you take a pairing interaction, then the wave functions conserve seniority. This was subsequently generalized by the school in Jerusalem, and in particular the students of Racah, so Talmi, Una, these people, they generalized this, and they showed actually that seniority is a much more general concept. And so they could derive the conditions for the conservation of seniority from a general two-body interaction. I will, in the next slides, show a few, and how I will try to indicate how it works. And so one result, which is known if you read textbooks, basic nuclear structure, Charmol theory, that if you take an arbitrary interaction between identical fermions, then this interaction will always conserve seniority if the fermions are sitting in an orbit with J smaller than or equal to 7/2. So let me, this is a little busy, but I will try to explain it, what is shown here. So this is this result, which is explained at length in the book of Darwin's simple models of complex nuclei. And so let me specify a two-body interaction by these matrix elements Vj here. So this is just a notation. You have, well, we assume that we place the nucleons, identical nucleons, in a single J shell, right? And so for a two-body matrix element, you can couple them to a total J, right, which must be even. And so your interaction is completely specified by those two-body matrix elements. Right? These coefficients A here, they're just numerical coefficients, so they involve the 6J symbol, but this is just a numerical coefficient. And so if your interaction conserves seniority, it should satisfy this identity. This is the condition which is derived in the book by Tan. And actually, this is, you can do this for fermions, you can also do it for bosons. It's basically the same derivation. So, what does that mean in a nuclear physics nuclear structure problem? So let's talk about lead-210, for instance. Lead-210 will be 2 neutrons in the G9-half orbit. So this is the experimental spectrum. From this experimental spectrum, you can derive the two-body matrix element here. They just, you can read it off. I mean, these are differences between the two-body matrix elements. This is what you get from the delta interaction, and this is what you have from the interaction. Okay? And so on the previous transparency was given a condition that those matrix elements should satisfy in order that the interaction conserves. Okay, so that's, for instance, the case. Let me show this result for J. It's 9/2, because this is the case I will later discuss in detail in connection with partial conservation of seniority. So if you have identical particles, so either neutrons or protons, in a J is 9/2, then these matrix elements, so you have matrix elements of the angular momentum coupled to 2, 4, 6, and 8, and so this linear combination of the matrix elements should be equal to 0. If this is the case, then your interaction conserves seniority. If it's not 0, it doesn't. Right? So you will be seniority mixed. And notice you can do the same thing for J-mus. 11, 13 is also valid for bosons. Okay, so then is seniority conserved in nuclei? This is also textbook material. So an interaction between nucleons is short range. A delta interaction is a reasonable approximation, and a delta interaction conserves seniority. One can show that. A pairing interaction is a further approximation. I have shown that a pairing interaction conserves seniority. And so, the sort of intuitively, it's very easily to argue that if you have a semi-magic nucleus, that means either neutrons or either active protons, seniority is a good approximation. And this is now sort of an accepted conclusion of nuclear physicists. Okay, this is also just historical remarks. So you have lots of experimental indications of this sometimes called nuclear superfluidity. And so if you have a pairing Hamiltonian, or if you have a Hamiltonian that conserves seniority, then in even nucleus, so the ground state will have seniority 0, and then you can show that the structure of this ground state is exactly given by the number of pairs, right? All coupled to 0, and so you have pairs n over 2 pairs of those, and this is the exact structure of the ground state. This will be the structure for the all mass nucleus. And so you can show that there are lots of experimental indications which have been verified over the years. Okay, so What about generalizations? So far I discussed what happens for a single J shell. This can be very easily generalized to degenerate J shells. It's a bit more complicated for non-degenerate J shells, so I will say a few words about that because there is recent work on that. And so for neutrons, for nuclei, of course, we have neutrons and protons, so you should also consider isospin, right? And that is a lot more complicated, but it can be done as well, as I will show in a few slides. Okay, so this is what to do. So how to understand actually seniority in the case of degenerate J shells. This was shown a long time ago, almost simultaneously by Kerman and Helmers. And so the relevant formalism is what is called quasi-spin algebras. So how does it work? Well, so we have our pair operator. So this is a pair operator where you put particles coupled to in several J shells. So you have a sum of all the J orbits which are available to your particles. And so this is a creation operator of such a correlated pair distributed over several orbits. And so your pairing interaction is of this form. And what is now the important issue here is that if you take the commutator of S plus, which creates a pair, and S minus, which annihilates a pair, then you find basically the number operator. So you find another operator, which I call Z here. And if you then compute, you find the same, the original operators again. I mean, in short, you have a closed algebraic structure. And it's because of this closure that you can solve this problem analytically. So this was shown by Kerman in the case of identical particles. By Helmers, he showed that this can be done for particles with intrinsic quantum numbers, like isospin. Okay, so this is a general trick, actually. Well, if the particles are not identical, then the algebra becomes more complicated, but it's still good. Okay, so now, so this, with this quasi-spin trick, this is a Hamiltonian that can be solved exactly. So this, the underlying symmetry will be SU2 quasi-spin symmetry. Can we do better than this? So what can we think as generalization? First of all, here you have a Hamiltonian where the orbits are degenerate in energy. So we want to have a situation where the orbits are non-degenerate, so you add a single particle term to your Hamiltonian. And then here you have a single strength for your pairing interaction, and it's known that this is actually not always the case, and that often the strength depends on the orbits where the particles are sitting. And so you have now, it would be nice if you can consider situations where you have a separable pairing interaction, but where the strength is dependent on the shell. And so then the question is this pairing Hamiltonian solvable? So I'm sort of, these are references where people have looked at these problems over the years. Okay, so is this pairing Hamiltonian solvable? Well, this is the answer. So this is actually, at the moment, there is no general solution of this problem. But three special cases have been solved. And so the first case, if you have a constant pairing strength, but non-degenerate orbits, and this was solved by Richardson actually a long time ago. So this can be completely solved. The second case, which was rather recently, so this is Span, and also Jerry Terray was involved in this about 10 years ago, is the other situation where you have different pairing strengths, but degenerate orbits. This is also solvable. And then the third case, and this was not so long ago, Alantic in Pelivan. If you have two levels, you can solve Hamiltonian completely, analytically. Okay, so this is sort of people doing this business. Now, an important complication in nuclei is pairing with neutrons and protons. And so, if you have neutrons and protons, then you can make two pairs actually. The first is isovector, so it's a spin singlet. So the spins of the particles are coupled to zero, so they're anti-parallel. And this, of course, needs to be the case for protons or for neutrons, but it can also be a state for a neutron or a proton. If you have a neutron and a proton, of course, the spins can be parallel, and that's a spin triplet, so which is S equals 1 and T equals 0. Okay? And so, if you have neutrons and protons, you have two channels, isoscalar and isovector pairing. And so, one can ask the question, well, can we treat pairing Hamiltonians with the two channels in the same way as we did for identical neutrons? This is an old problem. Again, it goes back to Raka. You see, Raka, there is a very, well, this is not your average reference, but I could get a copy of this, and indeed Raka discusses also this. But this is now a Hamiltonian, so an interaction where you have this isovector pairing with a particular strength, which I call G naught only, and this is the isoscalar pairing, which is G1. Okay. And so now you have a pairing Hamiltonian with two different strengths, which you can vary in principle. And so this, the problem that Raka considered was neutrons and protons with only isovector pairing, and then later Flower and Spikovsky considered isovector and isoscalar. And so this is essentially this quasi-spin trick, which I discussed in a simple case, can also apply here. Okay? And so in nuclei, actually, a reasonable, well, you can show that this Hamiltonian is solvable in three cases, namely if you have only isoscalar, only isovector pairing, or equal isoscalar and isovector pairing. And so for nuclei, the reasonable answer is actually that these are more or less equal. I mean, if you analyze shell model interactions, then you see that this is, well, actually the isoscalar pairing is slightly larger than the isovector pairing. But this is a reasonable answer. And then you can ask yourself, well, do we have any condensate structure for neutrons and protons, just as we had for identical fermions? That happens to be the case. And so this is, if you, I look here at the specific case of n equals n nuclei, right? And then if you have this pairing Hamiltonian, which I showed in the previous transparency, then the ground state of an n equals n nucleus has this form, right? And this is like a quartet. So this operator here will create two neutrons and two protons, and they are coupled to zero in spin, well, in angular momentum and in isoscale. And so this is like a quartet structure. This is like a condensate of alpha-like objects, right? And so this was shown by Daltones to be dealt here to be a reasonable approximation for all values of these two strengths G0 and G0, G0 and G1. This is a reasonable approximation of your true ground state. However, if you look at a realistic calculation, then it's very hard to find any evidence for a structure like that, because whatever you do, and especially if you add a spin orbit term to the Hamiltonian, then you will see that it reduces the isoscalar component, and you're left with the usual isovector component that you know for identical nucleus. Okay, so let me now tell you a little bit of more recent material, and this has to do with partial conservation of seniority. So what I showed previously is that in this analysis of let's say, of Raka, Tal, and Una, then you define conditions such that if two-body interaction satisfies those conditions, then all the eigenstates of this interaction will have good seniority. So they will carry good seniority. So now you can ask the question, well, is it possible to construct interactions where some of the eigenstates, but not all, have good seniority? And this happens to be the case. And so this was sort of discovered by Escuderos and Marizami a couple of years ago. And so they found numerically that if you have 4 particles in J is 9 halves, and identical particles, so eigeneutons or protons, and you couple them to 4 or to 6, then any interaction, any arbitrary interaction, will conserve seniority for those particular states. Right? So most of the states will be mixed in seniority except those 2 particular ones. And so they have wave functions which are independent of the interaction. So what I will show is that this is actually some relevance for seniority isomers. Okay, so just to give you a feeling of why this is sort of amazing, let's look at so this is not important all the numbers, but if you have 4 identical particles in G in 9 half shell, and you couple them to angular momentum, total angular momentum 4, so you have a matrix, and here are the matrix elements expressed, right, in terms of the two-body interaction matrix elements between the nucleons, right? And you see that this is, all of the matrix elements are non-zero in principle. So there isn't any of the matrix elements which is 0. So you would think that if you diagonalize this matrix, that you get a mess, that you get something which is very complicated, dependence on the matrix elements, the two-body matrix elements of the interaction. And actually this is not the case. What you find is that one of the eigenstates is always the same structure. So this is the structure for the state with J equals 4, angular momentum 4. It has always seniority 4, and it has this energy expression in terms of the two-body matrix. And this is the same thing for J equals 6, angular momentum 6. Okay? And so you notice that these are nice ratios of integers between the numerator and the denominator. So these are rational numbers, and there was a recent paper by Talby, so this is here a few months ago, and he showed that if the coefficients in front of those two-body matrix elements are rational numbers, then the state is solvable. And that means that this state is independent of the interaction. The energy, of course, is dependent on the interaction, but the structure of the state is always the same, independent of the interaction. So this is a particular example of this statement that was, or this proof that was given by Talon. So, what is the structure of those states? Well, here it is. So you for any interaction you care to choose, your 4 plus state will be, and you can calculate exactly the wave function. So this will be a d squared state. So for the people who like the interacting boson bonds, so this would be like a d squared state, which is coupling of 2 d bosons coupled to 4. But this is not a boson approximation, this is an exact Shelton result. Okay? And then there is a very small component where you couple a d pair with a g pair to 1 momentum 4. And I repeat, this is something which always should occur independent of the interaction that you put between the nucleons. And of course, if this state is always fixed, and the 6 plus state is always fixed, then the transition between the 2 states should be solvable and is always fixed and independent of the interaction. Okay, so this is sort of a little addition to this statement of Talby that as long as you have nucleons in a single shell up to 7 halves, any interaction conserves seniority. It just turns out that if you put them in house, that there are a couple of states which also conserve seniority. Okay? And you might say, well, this is again.
This statement that you made, that's only true for one of the J plus 4 states. Is that correct?
That is correct, yes.
Only one of them, and only for one of the J plus 6 states.
Exactly. So there are 3 4 plus states. Right? 2 of them will mix, but this one will be always separately.
Are they of necessity the lowest?
I will come to where they are in a moment. Because you might say, well, this is sort of neat, but rather academic, I mean, it's just one particular state. But it turns out it has some consequences for seniority. So, let me show some examples. So this is n equals 50 isotopes. So I will consider that the neutrons here are closed, 50 neutrons. And so the protons are in the G9 half from 42 to 48. Okay, molybdenum, platinum, cadmium. So what you can do, very simple-minded analysis, this is the experimental spectrum. You fix your 2 body weight examples from the spectrum, and then you go and see what happens for the 4 and the 6 particle states. 4 and 6 particle nuclei. And so this is what you obtain. And you see, this is the answer to your question. So this is the seniority 2 states here, 4 plus. It's not exactly seniority 2 because it will mix. But it will not mix with this one because this one is the solvable state which is hanging there and which is unperturbed by anyone. So this 4 plus will mix with the higher lying 4 plus state, about separated by 1 MeV. Right? But there is no mixing between those two 4 plus states. They are sort of independent. And so this is the seniority 4, which is solvable in the same structure. This is seniority 4, 6 plus solvable and always a constant structure. Okay, so this happens with 50 n equals 50 isotopes. Let me show a different example, and this is actually something which is measured or tries to measure because these are neutron-rich nickel isotopes. So nickel is Z equals 28, so it's close to the protons now. And people are interested in what happens if you put neutrons in the G9 half. So here this is done from nickel 70 up to nickel 76. Same kind of plot. And so now what you see is the solvable state. This is the seniority 4. This is seniority 2, right? Or almost seniority 2, a little bit mixed with a higher line 4 plus. This is exactly seniority 4. And so now the seniority 4 is below the seniority 2. Okay? So they switch. And I would say, I mean, what they measured is a 4 plus and a 6 plus. This, of course, you cannot know from the experiment like that. I would say this is probably seniority 4 plus and 6 plus, which has been measured. Okay, but is it important? Well, if you look at the decay, this matters. Because let me now compare the decay properties for the 2 systems. One system was platinum palladium, and the other system was the nickel isotopes. So in this system, if you look at the iris sequence, all the states, well, the ground state is seniority 0, not exactly, but close. And then all the other states, they have seniority 2. Right? Not exactly, but reasonably conserved by the interaction. And then there is a selection rule, a seniority selection rule for the E2 matrix element, which says that these E2 matrix elements are very small. Actually, they should be 0 in mid-shell. This is not mid-shell, but it's close to mid-shell, which will be 45. Right? So these E2 matrix elements are small. Okay? And this happens to the highest sequence. In the nickels, if you recall, the situation was different. Because in the nickels, the iris sequence was, well, this is seniority 4, seniority 4, and then the 8 plus again is seniority 2. So it's different. Okay, and that is reflected in the B2s, right? Because the B2s now are very large, almost. So what would be the conclusion? The conclusion is there should be seniority isomers here. Well, of course, this also depends on the relative energy, well, the energy difference between the 8 plus and the 6 plus. Usually this is very small. Here, that's a little bit unknown because this is seniority 2, this is seniority 4, so it depends on the details of the interaction. What will be the energy difference? But judging from the E2 matrix element is small, and here it is large. So here you should not have a seniority isomer. And actually, people looked for it, and apparently, so far they haven't found any seniority isomers in the nickel, whereas in the ruthenium palladium region, they're there and observed. So this would be a simple explanation of the occurrence of seniority.
These are experimental numbers.
These are calculated numbers in the seniority approximation. And experimentally, one do find an 8 plus, certainly an 8 plus isomer in both ruthenium 94 and palladium 96. It's there. There is an isomer, which means another small B2.